I welcome all of you to video lecture series on computational fluid dynamics, development, application and analysis. This is the lecture 2 of the chapter 1 of a companion book on Introduction to Computational Fluid Dynamics. This book consists of 3 parts. The first part is like building the foundation for the course, which consists of introductions and essentials. The part 2 enable you to develop CFD code or software for CFD problems in a Cartesian geometry. And the part 3 enable you to develop CFD software for complex geometry problems. The first chapter of this companion book basically answers the 3 questions which arises in mind for a subject. What is it, how it works, and why we are studying this subject. In the second lecture, we'll try to understand how CFD works. There are 3 elements of CFD which I had mentioned in my previous lecture. So as far as the working of CFD is concerned, the working will be discussed with respect to introduction to CFD development, introduction to CFD application, and introduction to CFD analysis. This lecture will be focused on introduction to CFD development. CFD involves 3 things: development of CFD software, application of the software to generate big data corresponding to the results for flow properties and engineering parameter. And finally, we create 2 types of movies from this data: scientifically exciting movies and engineering relevant movies. And through those movies, we try to analyze these results for an understanding of a fluid dynamics problem. The CFD development basically consists of 5 elements which will be presented in detail. The first element of CFD development is like a pixel generations. I mentioned in my previous lecture that this is a subject where you develop a product which is like a virtual video camera. The first step of the CFD development is like pixel generation, which here we call as grid generation. This is also called as preprocessor. The idea here is whenever we solve a fluid dynamics problem, the region on which we focus, we call that as a computational domain. And in this step of pixel generation or grid generation, we divide the computational domain into small regions, and we locate the grid points or pixels at the centroid of those control volumes. Now, as far as the problems in CFD is concerned, there are 2 classes of problems. Problems where the computational domain, the shape and size of the computational domain, if it is aligned along the standard coordinate system like Cartesian, cylindrical, and spherical, we call those as simple geometry problems. Otherwise, we call them as complex geometry problems. So the first step of CFD development, which is the grid generation, consists of, this is the simplest of grid generation procedure presented here. If you consider a flow region which is square in shape, then the simplest way of grid generation is we divide this region into small region by drawing equispaced horizontal and vertical line. Let us suppose this domain is of length L1 in the x direction and L2 in the y directions. So this is the simplest form of grid generations, where we draw equispaced horizontal and vertical line and divide this computational domain in which fluid flow or heat transfer is occurring into 25 small regions. Each of the small regions we call as control volumes. And we locate the grid points or pixels at the centroid of this control volume. So these are the 25 pixels or grid points located at the centroid of the 25 control volumes. Now, whenever you solve a fluid mechanics and heat transfer, you may have the problem in same shape and size of the computational domain, but you find that the results you can have a different results for depending on the boundary conditions. So you know that the boundary conditions plays an important role in the solution of the problem. So we also need to have grid points or pixels at the boundary of it. The grid points with the boundary of the domain is presented here for the left boundary, bottom boundary, right boundary, and top boundary. So here I am showing you two types of grid points or pixels. The yellow color grid points are called as internal grid points, and the blue grid points are called as boundary grid points. Note that we apply the conservation law to the small 25 control volumes for 25 yellow grid points or pixels, whereas we apply boundary conditions at this blue grid points. So whenever we do computations, we calculate the flow properties corresponding to this grid points, and we need to store the data corresponding to this grid points in a data structure. So one of the simplest data structure for this type of point distribution is matrix as a data structure. Now in a matrix, whenever we want to store the element of a matrix, we denote by some address. So the i's and j's are here represents the running indices corresponding to the element of the matrix as a data structure. So you can see here I is varying from 1, 2, 3, 4, 5, 6, 7. So I max is 7 in this case. Similarly, j is varying from 1 to 7 in the y direction. Whenever we do computations, later on I will show you that the governing equations in fluid mechanics, all of us know it's a partial differential equation. But the governing equation in computational fluid dynamics is a linear algebraic equations. So later on I'll show that the equations which we generate, it's a linear algebraic equations. And the equations are such that if there are 25 yellow pixels or grid points, we generate 25 linear algebraic equations by applying the conservation law to this 25 small control volumes. And in this case, we have 20 blue pixels or grid points, and we obtain the governing linear algebraic equation for this blue grid points from the boundary conditions. And when we derive linear algebraic equation for this yellow circles, later on I will show you that the equation is such that the value at a particular yellow circle, let us say temperature at a particular yellow circle, is a function of its north, south, and east-west neighbor, depending on a discretization procedure, which will be discussed later. So as mentioned, there are two types of grid points corresponding to boundary blue circles, and those which are interior inside the domain, we call this as interior grid points. I mentioned earlier that you have two types of problem: simple geometry problem and complex geometry problem. So this slide will show you the difference between the two types of problem. Let us suppose if I have a square plate with a square hole, then the point to note is that in this case you have two boundaries, one exterior boundary and second interior boundary. So the interior boundary is a square hole, and the exterior boundary is this shown by yellow rectangular picture. Both these boundaries are, since they are aligned along standard Cartesian coordinate system, either they are horizontal or vertical, this problem corresponds to a Cartesian geometry problem. If we have a circular plate with a circular hole, then in that case it's a cylindrical geometry problem. Okay, so for this case, what we can do is that we can generate grid where we draw equispaced horizontal and vertical line. Note that for a Cartesian geometry problem, we generate grid point by drawing equispaced horizontal and vertical lines to obtain the square computational control volumes. If you have a circular plate with a circular hole, note that in that case the grid generation involves concentric circles rather than the horizontal and vertical lines. So basically in that case we draw line with constant radius to obtain the various concentric circles for subdivision. Okay, now in this case, these are the grid points which are located inside the domain, represented here by yellow circle. And these are the grid points which are located on the left boundary, bottom boundary, right boundary, and top boundary. Note that here you have also an interior boundary. So these are the grid points corresponding to the boundary, which is corresponding to the hole. If you have a square plate with a circular hole, then you have the outer boundary is aligned along the Cartesian coordinate system, and the interior boundary is aligned along the cylindrical coordinate system. So this is a complex geometry problem. And because in this case, when you do the subdivision of the domain by using a grid generation procedure, the grid generation procedure which is shown here corresponds to a curvilinear grid generation, which will be discussed later in this course. So what we are basically doing is that in this case, we have obtained control volumes which are aligned along the Cartesian coordinate system. In this case, you obtain the small control volumes which are not aligned along any of the standard coordinate system, and this is a complex geometry problem. And these are the grid points located inside the computational domain, and these are the grid points located at the boundary of the computational domain. So this was all about the grid generation. Now, after the grid generation or pixel generation, the next step is, if we have, as I mentioned, if we have 25 yellow circles, we have to obtain 25 linear algebraic equations corresponding to those yellow circles. Basically, the second step involves algebraic formulations. Now, in these algebraic formulations, there are these algebraic formulations, traditionally it has been called as discretization method, because mathematically, as I mentioned, that the governing equations for CFD is a linear algebraic equations. So strictly, we need an algebraic formulation. However, historically, these algebraic formulations were done from the governing partial differential equations, and then they're called as discretization method. There are three types of commonly used discretization method, which basically generates the governing linear algebraic equations for the grid points which I had mentioned earlier. They are called as finite difference method, finite volume method, and finite element method. Out of this, finite difference and finite volume are more commonly used in fluid dynamics, and finite element method is commonly used in solid mechanics. And finite difference method is the oldest method for CFD, and finite volume method is a more recent method and which is used in most of the present day CFD software. And this algebraic formulation, as I mentioned, results in one linear algebraic equation for each grid points with unknowns as flow properties such as velocities, pressures, and temperatures. There are two types of approaches of finite volume method, which I'll discuss in detail in a separate slide. There is a traditional, in almost all the books of CFD, you will find they use a method which is called here as partial differential equation based finite volume method. And the companion book for this lecture series presents a methodology which involves a novel physical law based PDE free finite volume method. So all through this lecture series, we'll be following a physical law based finite volume method, which is an method for algebraic formulations generate the linear algebraic equations for the grid points, interior grid points. We'll use for the boundary grid points, we will use finite difference method. This is a schematic representation of the two approaches of finite volume method that I had mentioned. In your undergraduate courses on fluid mechanics and even in heat transfer, you start with the conservation laws. Like in first class of heat transfer, when the derivation is done for governing equations for heat conduction, 2D heat conduction, you take typically a control volume, and then you apply law of conservation of energy, where you express at the various surface of the control volume Qx, Qx plus Vx, Qy, Qy plus Dy. And then what you do is that you get a differential formulation. Basically, first you write capital Qx, and then you convert into small q, where small q corresponds to the heat flux. So capital Qx you write in terms of Qx, and in a 2D, the associated area is delta y. So you basically write, you multiply the fluxes with the surface area. Now get a differential formulation. What you basically do in not only in heat conduction but even in fluid mechanics, that you divide by volume, because any flux term multiplied by surface area divided by volume gives you a length scale in the denominator. So basically then you get Qx minus small qx plus delta x multiplied by delta y, which is the surface area for Qx, divided by the volume of the control volume. In 2D, the volume is delta x into delta y. Now the delta y cancels down and you get a delta x in the denominator. And then you're left with qx minus small qx plus delta x divided by delta x, limit delta x tends to 0. That leads you to del by del x of qx. So all the differential equations which you have derived in your undergraduate fluid mechanics as well as heat transfer course corresponds to the conservation law per unit volume. Because when you divide by volume, then only the flux, you get a gradient of flux terms. Because the surface area divided by volume gives you the length scale in the denominator, and the limit of that length scale give you the derivative. Almost all the books in computational fluid dynamics start with this governing partial differential equation. So any book on CFD, if you see, which uses a finite volume method or even a finite difference method, it starts with the governing partial differential equations for the to obtain the algebraic formulations for the yellow circles or the internal grid points, and for boundary grid points, finite difference method is used. So for almost all the books on finite volume method, they start with this governing partial differential equation. So that's why I am calling this as partial differential equation based finite volume method. So this governing partial differential equation, note that which we call as Navier-Stokes equations, which is a combination of continuity, momentum, and energy equations, which we derive from the conservation laws. Now, almost all the book on based on finite volume method start with this governing partial differential equations. Then they use a mathematical procedure. First, they do a volume integral, and for certain terms, Gauss divergence theorem is used. Along with certain approximation, finally they lead to a discretized linear algebraic equations. So this is one of the procedures which you find in almost all the books in which uses the finite volume method for CFD. However, based on my teaching experience, I had realized that the student, especially the undergraduate student, the early undergraduate students, struggle to appreciate the Gauss divergence theorem and get a feel of this linear algebraic formulations. So in the companion textbook which are corresponding to this lecture series, a novel physical law based finite volume method is proposed, which is a PD free. So this in this book you will not see that the CFD book will not start from the partial differential equation. It starts with the conservation law or the physical law, which are like mother for the derivation, not only for the partial differential equations, but also for the linear algebraic equation. It is like the partial differential equations are the elder brothers and the linear algebraic equations are the younger brother, which came into existence only after the advent of computers. And probably we have been too fascinated with for generations or with the continuous math, and when the finite volume method was proposed, people thought there is no other way than to start with the continuous math using the governing partial differential equation to derive the linear algebraic equation. However, when finite volume method was proposed, there was an alternate, more I would say more physical approach based finite volume method could have been proposed, which is presented here. This physical law based finite volume method start with the conservation law, and in fact it starts with the same control volume which in the undergraduate courses you start to derive the differential equations. So so using the same control volume and the same conservation law from which you have derived the differential equations, we start, and then using in this case we don't use any volume integral or Gauss divergence theorem, because in this we use an approach, we use a discrete math independent of continuous math, and using the two approximations are very similar to the approximations which are presented in the alternative approach, and using the approximations we derive the same set of linear algebraic equations. So you can obtain the same set of linear algebraic equation either following this approach, which uses the governing partial differential equation, whereas this is a more physical approach where you apply the take the control volume, apply the conservation law along with the approximation, and come up with the same set of linear algebraic equations. The approach which was presented here has also been found in the literature. This is a paper which was published around the time when I was writing this textbook. This paper was written in 2013, where the author, Professor Tonti, uh, in one of the best journal in computational fluid, Journal of Computational Physics, he had a paper. The title of the paper, I was very pleased to see that the title was very similar to what I had come, the idea with which I was proposing this physical law-based finite volume method. The title is Why Starting from Differential Equation for Computational Physics. So, as I said in my previous slide, that these are the two approaches, and this paper questions the approach followed with starting with the partial differential equations to derive the linear algebraic equations. In the abstract of this paper, it is mentioned that we can get an algebraic formulation avoiding any arbitrary process of discretization of differential equations. So they have called this discretization procedure as an arbitrary procedure. And so there is an alternate procedure they are saying, and this procedure, this formulation has great merit in maintaining close contact between the mathematical description and physical phenomena. All the statements I have taken from the abstract from this paper. Professor Tonti has further mentioned in the earlier paper that the exact solution that is promised by the differential formulation is hardly ever attained in practice. By contrast, the great technological progress in nowadays is made possible by the fact of being able to have an approximate solution. So what is basically highlighting is that we have been probably too fond of differential formulation, but if you look into the practical applications, we hardly have obtained an analytical solution for most of the real world problems. And for most of the real world problems, what we have been able to find is an approximate solution, which is from CFD. So that's why we have been able to obtain, as I had mentioned in my earlier lecture, that we have been able to obtain approximate solution. I had mentioned and made a statement in my previous lecture that numerical solution is like finite resolution virtual video camera. So CFD is like a finite resolution virtual video camera, whereas analytical solution is like a infinite resolution virtual video camera. But we hardly have ever attained to obtain solution of the analytical solutions. Another researcher, Desburn, in a research paper in 2005, you can read this statement which he has made. So, so in this paper, they have highlighted that probably we have been addicted to our habits of considering the differential or continuous formulation as indispensable. We have been using continuous math or differential calculus for generations, and we have been habituated to consider that algebraic formulation has to start with this differential formulation. So in this paper, he has mentioned that if we can work with discrete math independent of continuous math for algebraic formulation, it will lead to an increase as well as enrichment in the range of applications. Finally, the discrete independent of continuous math based approach will also lead to a much physical understanding as well as better developments of simulation methodology in various branches of science and engineering. So with all this discussion, what we are basically highlighting, what is basically highlighted is that the algebraic formulation which will be presented in this lecture series will follow the discrete math independent of continuous math so that you get a much better appreciation of the algebraic formulation. Finally, so after the pixel generation, the second step, as I mentioned, was algebraic formulation. So if there we have 25 yellow circles, by using this physical law-based finite volume method, 25 linear algebraic equations are derived. And for the 20 blue circles, which I had mentioned in the grid generation, the linear algebraic formulation involves finite difference. Once you have obtained this system of algebraic equations corresponding to the yellow pixels and the blue pixels, then the next step is solution methodology. So we have to solve the system of algebraic equations. Note that the number of algebraic equations is equal to the number of unknowns. So you have the solution methodology consists of there are two methods of solving the system of linear algebraic equation. One is called as direct method, where you take the basically a linear algebraic equation can be expressed as a coefficient matrix multiplied by the unknown vector is equals to the constant vector, and you can take the inverse of the coefficient matrix multiplied by the constant vector to get the unknown vector. This method is called as direct method. However, in most of the computational courses, not only in computational fluid dynamics, but even in finite element methods, we follow another approach of solving the system of algebraic equation, which is called as indirect method or an iterative method. So there are three steps of solution methodology. First step is basically you have a method to solve the system of algebraic equation. If you use an unsteady state formulation, there are two types of method. This will be more clear later on in the course: explicit method and an implicit method. And if you are using a steady state formulation, then there is an iterative method, is the solution method. Along with the solution method, another extremely important thing is the implementation detail. Because solution method, it's like if you are made to learn what are the different parts of the car and what are the principle of operations of the different components of the car, it's very difficult for you to make a car unless somebody tells you what are the nuts and bolts which are required to make a car. Similarly, if we want to learn to develop a CFD software, it's extremely important that along with the solution method, in this solution methodology, you are provided the nuts and bolts which are needed to develop this software, which basically in computational development consists of data structure and the loops. So the data structure and the loops corresponds to the implementation details, and which will be presented in the, after the solution methodology. And finally, there is a solution algorithm, which is a step-by-step procedure to solve the system of algebraic equations along with the solution method. Note that in almost all the books in CFD, the solution method and solution algorithm are there, but the novelty corresponding to the companion textbook is the implementation details, which clearly presents the data structure and the loops which are required to, which gives you the nuts and bolts to develop the CFD software. Here I'll present this. This is an introduction to CFD development. So I will show you the solution methodology or solver development just in one slide. So let us take the simplest of problem. Like if you consider a heat conduction in your undergraduate course, the simplest of problem was left wall 0 degree, right wall 100 degree, and you take a thin plate and you solve it as a 1D heat conduction problem. Now for a computational fluid dynamics, this is like similar to that problem, the first problem, the very simple and elementary problem. Let us consider a plate whose left wall is maintained at 100 degrees centigrade, bottom wall is maintained at 200 degrees centigrade, right wall is maintained at 300 degrees centigrade, and top wall is maintained at 400 degrees centigrade. So with this boundary condition, you already know the temperature of the blue circle on the left wall is 100, bottom wall is 200, right wall it is 300, and top wall it is 400. Now, what is the temperature of the yellow circle? Now, the boundary conditions gives you the temperature of the boundary points at all times, whereas the temperature of the first picture of the yellow circle is known from the initial condition in an unsteady problem. So let us suppose if I have taken this plate from a furnace at 250 degrees centigrade. So initially this plate is at 250 degrees centigrade and it is subjected to a boundary condition: left wall 100, bottom wall 200, right wall 300, top wall 400. So note that from the initial condition, I know the temperature of all this yellow circle as 250 degrees centigrade. And from the boundary condition, I know the temperature of the blue circle. So note that the temperature of the first picture in any CFD simulation for unsteady case is known from the initial condition and boundary condition. So the procedure which we use in our solution methodology is we know the data, note that the data is discrete in nature, such as in this case there are 9 grid points, 9 yellow circles, and there are 12 blue circles. So from the initial condition and boundary condition, we already know the discrete temperature distribution, grid point by grid point temperature distribution, and we use a solution methodology where so we know the temperature of the first picture, and we have come up with an algebraic formulation. Note that the algebraic formulation is such that the temperature, right now what I am showing is like a schematic representation of the algebraic formulation. The algebraic formulation is expressed in such a way that if this is a point P, what we do is that, just to give an example, if this point is called as P, this point is towards the east side of it, this is west side, this is north, this is south. So we obtain an expression, or linear algebraic equation is such, and here the power n plus 1 corresponds to the superscript temperature here is n, the superscript of temperature here is n plus 1. And note that this NB is neighbors, the neighbors corresponding to east, west, north, and south. So the formula the algebraic formulations which we obtained to obtain the temperature of the new picture in an explicit method is such that the temperature at this point is a function of this 5 points. Okay, so in any computational course, note that we derive algebraic formulation. We only derive an algebraic formulation. In your undergraduate courses, you have one formula, and basically you take the help of calculator to obtain the solution. In computational course, note that when we do algebraic formulation, we also derive only one formula. What I'm trying to say is that we will, later on I will show you, although there are 9 yellow circles, but we will express the linear algebraic equation corresponding to this 9 yellow circle by a single formula. Now, there's a difference between these two formulas. The difference is something like this. Like in your undergraduate course or any analytical course, you have a formula like Z is equals to X into Y. Okay. Whereas in any computational course, we also have a very similar formula. Z is equals to X into Y. But this formula is written in matrix form. Like Z, you can have an argument inside bracket, Zi is equals to Xi into Yi. Okay, so note that the computational course, although there are a lot of details, but as far as the formulation is concerned, in your analytical heat conduction course or analytical fluid dynamics course, you have one formula. In a computational course also, there can be millions of yellow circles, but the algebraic formulation which we derive is written in data structure form. It is written in matrix form, and we apply, like in this case, we have one formula which is written in indicial form. In this, it's a 2D problem, so it's written as I comma j, and then that formula we use a loop. Like in this case, for I, this is I is equals to 1, I is equals to 2, that this is I 3, I is equals to 4, I is equals to 5. So this is I to J2. So we use a loop to scroll through all these 9 points, I varying from 2 to 4, J varying from 2 to 4, and we have inside that loop, we have only one formula, Ti comma j as a function of Ti plus 1 comma j, Ti minus 1 comma j, Ti comma j plus 1, Ti comma j minus 1, but that corresponding to previous picture. So this is a schematic representation of the formula corresponding to this yellow circle. Now, this is corresponding to I is equals to 2, j is equals to 2. Now, when this the loop goes ahead, it will go ahead means j is equals to 2, I is equals to 3. Then the formula is such that these 5 values are used. So this is a schematic representation of when you use a loop and when you express your algebraic formulation in an indicial form. This is an animated representation of how do you obtain the data for the second picture from the data of the first picture. And once you know the data of the second picture, you obtain the data for the third picture. As I mentioned in the previous lecture, there is a time step between these two pictures, where I have drawn analogy with the frame rate of the video camera. Here we call that time difference as time step. So from the first picture which we have obtained from initial condition and boundary condition, using the algebraic formulation, the data for the second picture is obtained. From the data of the second picture, the data of the third picture is obtained, and this picture by picture create the animation of temperature distribution or temperature contour for this heat conduction problem, which I will be presenting later. So after the pixel generation and the algebraic formulation and the solution, note that the solution methodology which I presented was for a heat conduction, and right now you have only obtained the temperature distribution. Now I have mentioned that with this you can create a movie for temperature distribution, which is a scientifically exciting movie. But as an engineer, you are not only satisfied with temperature distribution. As an engineer, you also want to know the rate of heat transfer. Now, to obtain the rate of heat transfer, after you have obtained the temperature distribution, there is another procedure which is the step 4 of CFD development, where you compute the engineering parameter. This is also called as post-processing. Now, to calculate the, I'll take an example of heat conduction to discuss this point. So you have to do a numerical differentiation and a numerical integration. Let me go to the problem and then you will be able to appreciate. So as I mentioned, that let us suppose you are solving a heat conduction problem, and let us suppose this is a plate, and you know the temperature distribution after the solution from the solution methodology. And once you know the temperature distribution, let us suppose you want to know the total rate of heat transfer from the bottom wall of this plate. Now to calculate the rate of heat transfer, first you will calculate the heat fluxes. You will calculate the Qy at this blue circle, and then you will calculate Qy here, here, and here. Once you know the heat fluxes corresponding to, so what you are basically doing is that the heat flux which you obtained here will multiply by this surface area. This heat flux you will multiply by this surface area, which is a delta x in this case. And then you have to do a numerical integration to calculate the total rate of heat transfer. To calculate Qy here, you use a Fourier law of heat conduction minus k dt by dy. Now you have a temperature distribution here, not in a functional form, you have it in terms of a discrete data. So one of the simplest approach to calculate dt by dy here is that you take the temperature of this point, subtract the temperature of this point, and divide by the distance between these 2 points. Okay, so temperature at this point minus temperature of this yellow circle minus temperature of this blue circle divided by the distance between these 2 points gives you an approximate representation of, which is the first order accurate, which I will discuss little later. Similarly, you obtain Qy here, Qy here, and Qy here. Once you obtain Qy at this 4 boundary grid points, you can multiply by the respective surface area, which is, and then sum it up, which is a numerical integration. Similarly, if you take a problem, let us suppose you have a box in which the top wall is like a conveyor belt moving from left to right. Then the fluid inside this will start rotating in clockwise direction. And once you know, let us suppose you know the velocity distribution at all these circles, then you can um, let us suppose in this case, instead of heat flux, you need to calculate wall shear stress and finally the total shear force, which is an engineering parameter for a fluid mechanics problem. Now, to calculate shear stress in this, you need shear stress are basically represented by the normal gradient of tangential velocity. So, to calculate shear stress on the bottom wall, it will involve del u by del y. So, again, similar to dt by dy here you have del t by del u by del y, which you can calculate by numerical differentiation. And finally, once you obtain all the stresses, you can use numerical integration to calculate the stresses, from the stresses to calculate the shear force. The last step of the CFD development, which is the fifth step, is note that the grid generation is like a pixel generation, and the algebraic formulation corresponds to the number of algebraic formulations where you obtain the number of algebraic equation equal to number of grid points. And once you obtain this algebraic formulation is like a pen and paper work. Once you obtain the algebraic formulations, you go for the solution methodology, and from the solution methodology, note that you obtain the solution only for the for flow properties at yellow circles, as well as blue circles corresponding to the flow properties. But you do not get the engineering parameter. For engineering parameter, you have a separate step where you do numerical differentiation and numerical integration to calculate the engineering parameter, like in conduction. First you calculate heat fluxes at the boundary grid points, and then finally calculate the total rate of heat transfer by numerical integrations. Similarly, in the fluid mechanics problem, I had shown you that you can calculate wall shear stress and finally to calculate the total shear force. So note that in the third step, you obtain flow properties from which you can create scientifically exciting movie. From the fourth step, you obtain the engineering parameter from which you can obtain an engineering relevant movies. And when you play both these movies together, you can get a scientifically exciting and engineering relevant analysis of this problem. But once you do this development, any development cycle is not complete unless it goes through a rigorous testing. So in computational fluid dynamics, once you have developed your computer program, then you test it on certain standard problems. And if you compare your results, if you are comparing your results with some already developed code or a software or with some published analytical solution, then it is called as verification, code verification. Whereas if you compare your numerical results with some experimental results, then it is called as validation. So these are the 5 different steps of CFD development. With this, I had come to the end of this lecture on CFD development, and the next lecture will be on Introduction to CFD Analysis. This is a reference book, and you can get more details about this lecture from this book.